Photoplethysmography, signal processing. The webinar is hosted by the Institute of Physics and Engineering in Medicine, or IPEM. And may I extend my thanks to James, Catherine, and others at IPEM who have made today's webinar possible. The webinar is being recorded and will be made available on the IPEM website. A link will be sent to registered delegates as soon as it's available to view. Today, we have 3 talks given by Dr. Zairong Ding, Ariane Marassi-Sasu, and Serena Zanelli. Together, they will cover key topics in photoplethysmography signal processing, including blood pressure estimation, signal quality assessment, deep learning, and pulse wave analysis. During their talks, we encourage you to contribute questions using the Q&A or the chat box at the bottom of your screen. And so it gives me great pleasure to introduce our first speaker, Dr. Zairong Ding. Zairong is a research associate professor at the University of Electronic Science and Technology of China. Her research interests are in wearable medical devices, biomedical signal processing, health informatics, and artificial intelligence for healthcare. She has a wealth of experience in estimating blood pressure from the photoplethysmogram, and today Zairong will be presenting on exploiting photoplethysmogram features for cuffless blood pressure estimation. Zairong, thank you very much for speaking to us today. We're very much looking forward to your presentation. Zairong, I think you're muted.
Okay, so thank you so much, Peter, for your very kind introduction. And it is a great honor to get invited to share our work on exploiting the PPG features for the cuffless blood pressure estimation. So all clear, right? The presentation you can see. Okay, so we know that the cardiovascular disease is the leading cause of death. So in the year of 2019, according to the WHO data, about 32% of deaths was attributable to the cardiovascular disease. And for the cardiovascular disease, we know that the hypertension, the high blood pressure, is a major modifiable risk factor for it. And also there are studies shows that the blood pressure variability is associated with increased risk of cardiovascular disease and in patients with hypertension. So it is very important to monitor blood pressure and the dynamic blood pressure to get early prediction and early detection and prevention of hypertension and the hypertension-related cardiovascular disease. So the blood pressure measurement techniques, so for currently the techniques we can divide it into the 2 dimensions, whether it's invasive or non-invasive, or if it is intrusive or unobtrusive. So of course, for invasive methods like the implantable finger sensors and the intra-arterial way, so they are not suitable for daily use, right? And also the common use that I think most of us know that the oscillometric monitor is the most popular one used in our daily life. But this kind of technology, they can only provide a snapshot of our blood pressure value. But so there are also techniques, including the volume clamp methods, the telemetry technology, but they can provide continuous reading of blood pressure non-invasively. But the challenge is that they are quite large size, and also they require the professionals to operate the system. And also it is, of course, very high expensive. So the most promising ways, of course, that is non-invasive as well as unobtrusive. So we can use it for everywhere and at any time. This is also that this technology can get rid of the cuff. So we use a limit as cuffless blood pressure monitor. So this is implemented by integrating small sensors like the wearable sensors or the epidermal sensors and onto our daily gadgets like a watch, or we can also like integrate it into our daily object like the furniture, the chairs, as well as the bed. And currently for the blood pressure estimation, we know that the wearable PPG, this technology has been commonly studied for the cuffless blood pressure estimation. And the hypothesis is that we think there is a collection or there's a mapping function between the wearable non-invasive cardiovascular signals and the blood pressure. And usually we would build models, either the mechanical model or the data-driven model, to mapping the signals to the blood pressure. But the bridge is the features that can evaluate the blood pressure changes. So normally we would use hand-designed features and develop physiological models to do the estimation. In the recent years, we also try to develop data-driven models, like the deep learning models that our speaker will introduce later about this. So either for these two models, I think the blood pressure feature that gets extracted from the wearable signals is the bridge between the PPG signal, like or other signals, and the blood pressure estimation. And for blood pressure, as I just mentioned, the PPG is the most popular used signal. And the well-known indicator, the pulse transit time, has been used to track the blood pressure changes. So the pulse transit time can calculate it from the PPG signals, like two channels PPG signals, or the PPG signals and the ECG signals. And according to the principles of pulse wave velocity reporting, and then we can build a mapping function between the pulse transit time and the blood pressure. So by calibration or under some hypothesis or assumptions and then we can get the blood pressure with the calculation of pulse transit time. But the problem is that even though the pulse transit time has been very widely studied for the blood pressure estimation, but the major challenge is that with single pulse transit time, there is very limited accuracy for the BP estimation. And the major reason, as we know, is that the pulse transit time can only reflect some factors that affect the blood pressure changes. Say the pulse transit time can evaluate the arterial stiffness, but except for the arterial stiffness, there are also other factors that can affect the blood pressure. So there is a need to explore the extra indicators that can reflect a spectrum of blood pressure changes. And in this talk, I will just introduce some of the work that is based on the feature extractions from the pulse transit from the PPG signal. So one of our study is that we derived a new indicator, the PPG intensity ratio. We name it PIR from the PPG signal. So the basis is that we know the arterial diameter would vary with arterial pressure, as you may see from this figure, and also with PPG signal, the formation of PPG signals, we know that it is based on the Beard number law, right? Here we know that the L is the effective night pass, and the PPG signal basically reflects the blood volume, and the blood volume is actually changing with the diameter change of the blood vessel. So we would derive the intensity, the PPG intensity, while the blood pressure is at the diastolic status and the systolic status. And with some derivations and calculations, we can get the diameter change based on the ratio of the high intensity and the low intensity. So here we could say that the PIR could potentially reflect the relative change of the arterial diameter. And so we also did experiments and did comparisons about the PIR with the other indicators like pulse frequency time and the heart rate intervals, and calculated their spectrum and say, so this is a spectrum for these indicators and the different status, say the rest, deep breathing, Valsalva manual, and the hand grip test. So as you can see this figure, so the PTT can reflect the high frequency of the blood pressure, and the PIR actually could reflect the low frequency of the blood pressure change, as well as the high blood pressure change. So based on this, we derived a new blood pressure estimation model based on the MK equation and the window castle model. So because of the limit of time, so I only showed the model here. And also we compared the models with that is developed with PIR and the PTT, and compared with the models that's using only the PTT. And this figure shows our proposed method, the estimation by this method and the reference blood pressure. And this is the comparison of the proposed method with these two PTT methods. And we can see that the accuracy is significantly improved. But still, this accuracy cannot meet the clinical standard. So we aim to explore further, even more features from the PPG signals. So we did the work with extraction about 7 classes of features, including the PTT, the pulse-wise, and some meaningful relative index from the ECG and the first and second derivative of the PPG signals. And then we evaluated the relationship between the PPG features and the blood pressure with 3 methods. One is the correlation coefficient, and second, the mutual information, and as well as the cross-sample entropy. So this method could evaluate their no matter the relationships is linear or nonlinear, and also they can compare this synchronizations between these 2 time series. So this is results showing the correlations of the 222 features. So I listed as the x-axis, and their relationship with blood pressure components, the SBP to the pulse pressure. And this is also evaluated at different sites of the artery. So the peripheral artery at the radial artery, and the central artery while at the rest, and while at administering the nitroglycerin, the drug. So we can say that the coefficient between these features and the blood pressures actually varied at different sites. So it's different at the peripheral and at the central, and also at different status, like at either at rest and the drug admin status, they are actually different. And there are quite few features that vary consistently with blood pressure. So this is a bit challenging that I will mention a bit later. So with the combination of the 3 methods I just mentioned, we selected 5 best features for the systolic and the diastolic blood pressure. And we can say for the systolic blood pressure, actually the pulse frequency time is not the best. And for the systolic blood pressure, we found the pulse-wise features class, in particular the pulse-wise at the half amplitude of the PPG had the highest correlation coefficient and the lowest cross-sample entropy and the highest mutual information. And for diastolic blood pressure, the amplitude, the intensity, and some index ratio could best reflect the DBP change. And this is an example for the relationship of the explored features and the systolic blood pressure. So as 3 dimensions for the different methods. And here, for this, again, we can say that the pulse-wise, this class of features could better evaluate the blood pressure changes when administered with nitroglycerin. So for this studies, actually, we could evaluate their relationship, but still we are not sure that whether they have some causal relationship with the blood pressure. So we further dived into this issue by identifying features that would causally related with the blood pressure with fast causal inference algorithm. steer from these 222 features. And this is the strategy that we use. So basically for the fast causal inference, we would test whether the variable X and Y, here X and Y is the feature, PPG features and the blood pressure. We test if they are independent given the variable set. And the variable set is all the variable except X and Y. And we got the causal graph for the systolic and blood pressure, systolic and the diastolic blood pressure. And here we can say that the pulse transist time calculated from the R peak of the ECG to the derivative of the PPG peak actually is kind of causally related with SBP and the DBP. But in addition to the pulse transist time, we also got the amplitude features that would causally related to the systolic blood pressure. And here in this causal graph, we could not find the pulse wave, the PWHA, as I mentioned earlier, right? This is potentially due to that the data, because we use different set of data. So for the first part of the study, we use the invasive blood pressure that collected from the clinical setting. And for this one, we did experiment in our lab. And we still have experiments undergoing on to figure out this. And these are four features that are causally related with systolic and diastolic blood pressure. So the causal link is detected with the PCMCI algorithm. And here the index 0 means the time lag between the features and the blood pressure. And to further explore whether the causal features would help to estimate the blood pressure, we just simply develop some simple machine learning regression models to say their estimation performance. And we found that for the XG boost, it can give the estimation standard deviation derivation about 4 millimeter mercuries. And for DBP, it can get about 2 millimeter mercuries. And the comparison about these features with other features, so this part of work is also undergoing. And so briefly, so in the brief summary is that we explored new features in addition to the pulse transist time, like the PIR and some new features for the cufflinks blood estimation. But there are still some major challenges. In particular, we know that the relationship between the features and the blood pressure, there exists the inter and the intra-individual differences. So as well, also, is a different status, the relationship would vary. So this is a challenge. And also the further work is that we need to build mechanism-based estimation model with the identified features. So this is the ultimate goal. So that is all. So I would like to thank my collaborators and my group, as well as the research founder. So thank you very much for your attention.
Thank you very much indeed, Zairon. Fascinating talk and a fantastic body of work.
Thank you.
If anyone has any questions, feel free to contribute them. In the meantime, could I ask, right towards the start of your presentation, you suggested that there could be a function which related the PPG to blood pressure on the previous slide.
Yeah.
Do you think it's true? Do you think a PPG signal contains everything you need to know to be able to get to the blood pressure?
This is really, really a good question. And I also think a lot and still thinking about this. So to be honest, for the last work that I introduced the causal inference. So one major reason for that part of work is that we would like to figure out whether the information in the PPG signal is actually causally related with the blood pressure. So I think the answer, I would doubt that whether there is yes or no, but actually at the current stage, I only doubt, but I couldn't get a confirmative answer. Thank you.
Thank you. We look forward to reading more of your findings in due course. We have a second question from Alex, who has a question about the results you showed just towards the end of your presentation. And he or she refers to the mean error and standard deviation and asks, are these for the calibration-based model or for a calibration-free model?
So at the end of this study, because we just built, so actually if we identify the causal features, the best way is to build the mechanism model, right? Because it is we thought it is causal features, but to find the mechanism models it needs time. So also we have work undergoing to do that. But for this part of results, it is using the data-driven model, which is machine learning. So it is calibration free.
Thank you. And one further question from Talansh Batra, who asks, how would you go about approaching inter and intra-individual differences for blood pressure estimation?
Yeah, this is also quite good, great question. And actually for cuffless blood pressure estimation, I assume the inter and the intra individual differences is the major challenges. So from my point of view, I think there is not yet a true or good accurate features that can reflect the blood pressure. That is why it reflects the inter and the intra-individual. So I assume that if there is an accurate feature, it can reflect the blood pressure. I think the inter and the intra-individual difference would disappear. Yeah, I hope I answered the question.
Thank you. We have two more quick questions, if we may. Firstly, from Ramu Pitala, have you explored any features related to phase difference of PPG?
Sorry, you mean the limited?
Yeah, I'm not entirely sure what you're referring to by phase difference. Perhaps shall we return to this, Ramu? If you would like to just expand on what you mean by phase difference, perhaps we'll come back to this question. And in the meantime, Zyron, perhaps we could move on to Taerim's question, which is, how can we overcome the limitations of photoplethysmography to identify extensive cardiovascular diseases through wearable devices?
The limitation, yeah, thank you for your question. The limitation of PPG, I think it is really depends on what do you use it for. So if we would like to use it to evaluate the heart rate, as we say, I think currently quite a lot of wearable consumers can already done that. But if we would like to use it for other functions, for example, the blood pressures and other parameter monitoring, and then the limitation would be quite different. So for blood pressure specifically, the limitation could be the motion artifact. So this is one of quite practical issues. And later, maybe Erin or Seren, I couldn't remember, will introduce their work on this. So this is one challenge. And the other limitation is that actually Peter at an earlier time just asked the question, the key question is whether the PPG could give the information for us to do that. And we need to figure out that.
Thank you.
Thank you.
So one final question before we move on to Ariane. Ramu has clarified that he is asking, have you explored any features related to the phase difference between two PPG signals?
You mean how to phase PPG signal, right?
So I think, for instance, imagine that you measured two PPG signals at different sites on the body, or perhaps using different wavelengths. Yeah.
Oh, I see. I think if you got two channels of PPG, either two channels at different sites with the same wavelengths or different wavelengths, as I just mentioned, you could explore. You can try all kinds of features if you just would like to do exploration, like in the time domain, as I just did for the work I just introduced. as well as spectral domain, features in spectral domain, as well as some nonlinear dynamic features. You can extract the features from each channel or each wavelength of the PPG. I think that is a possible way.
Fantastic. Well, thank you, Zairong. Thank you for a fascinating presentation and for in-depth answers to a range of questions. Much appreciated.
Great. Thank you so much again for your invitation. Thank you.
So next, we will move on to Ariane's talk. Ariane, sorry, I'm just going to spotlight you. Ariane, welcome. Just to introduce you, our next speaker is Ariane Marassi-Sassou. Ariane is nearing the end of her PhD at the Digital Health Center of the Hasso-Plattner Institute in Germany. Her research focuses on digital health and personalized medicine, analyzing wearable data and using machine learning to understand chronic diseases such as hypertension. Today, Ariane will be presenting on evaluating machine learning models for blood pressure estimation from photoplethysmography beyond intensive care. Thank you very much, Ariane.
Thank you, Peter, for the introduction and the invitation. Of course, I'm really happy to be here. Also, thank you, Professor Ding, for the amazing lecture and also for introducing the topic. I realized that I didn't cover that much in my presentation, so that's great. I will share my screen now. I hope everything goes well. Can you see it? Yes. Yeah. So as Peter said, my name is Ariane. I'm from the Hasso-Plattner Institute in Germany, and I'm going to talk a little bit about how to evaluate machine learning models for blood pressure estimation beyond intensive care. But before I dive into this topic, I just wanted to show our institute a little bit. I mean, most people never heard of it probably, but it's actually part of University of Potsdam. It's a public institute, and it has 3 chairs. One of them is personalized medicine, the chair which I'm part of, which is led by Professor Evan Bettinger. I'm also happy to talk to anyone who's curious about the institute. So I brought this picture just so you know who we are. Well, now going more directly to the topic of this talk, I have a few points that I want to cover. So I'll talk a little bit about PPG data, the experimental design of this study, how we did the model selection, parameter selection, and final evaluation. So first of all, I think you probably already know what is PPG data. And here I want to focus a bit more on how you can get this type of data from wearable devices. So you see on the left hand side, a wearable, this is the Empatica E4 device. You see a bunch of LEDs there, and that's how you can get the data on the right hand side. So basically the light goes through your skin and it goes inside your blood vessels, inside they're absorbed or reflected by your hemoglobins. And that's how you can measure the flow of blood. And that's how most modern wearables measure, for example, heart rate. In my case, I'm kind of studying more blood pressure estimation. So I'm trying to see if we can extract features from this data to actually estimate blood pressure. So for this study particularly, we use 3 data sets. So you can see here on the left-hand side, 3 different data sets. The first one I named HYPE. This is one data set already collected here in Germany, and the 2 other ones were publicly available data set. The name of this talk is PPG, blood pressure estimation from PPG beyond intensive care, because I have seen a lot of work done, especially in the MIMIC data set, right? It's data collected from intensive care. And we wanted to see, okay, how well different models perform in data that is not collected in the ICUs or intensive care, and also collected during movement. So basically we have those data sets. First, we start with our own collected data set. I'll talk a bit more about the data sets in the next slide, but we do some signal processing, we extract some features, then we select the best model that works in our data set, and then we try to evaluate that model into other data sets. So here I have a brief description of the different ones. So the HYPE data set is something we collected here in Germany. So in the Charité hospital, we did actually, it's a data set composed of two different experiments. So one was a stress test where we had people with hypertension to rest, then do some exercise and then rest again. And then we would measure their blood pressure and PPG before and after the exercise. And then we gave them the devices and they used them for 24 hours. And we would get this data back together with blood pressure measurements. Of course, the blood pressure was not measured continuously because we were using a oscillometric device. So it's also a bit different from the ICU where you can get invasive blood pressure and then point-to-point blood pressure measurements. And then we got these two other data sets from the literature, one with individuals with normal blood pressure during a stress test as well. They were running a treadmill and then their blood pressure was measured before, after the exercise. And later we have another data set with more than 200 patients or people, not just patients, but measured in a control experiment during rest. And for that data set, we had subjects with hypertension, without hypertension, and even pre-hypertensive. We started actually not just with this hypothesis that we wanted to measure blood pressure in daily life, but also not just with normal individuals with normal blood pressure, but also with hypertension. That's why we collect the HYPE data set, and then we use two other data sets with different types of individuals to validate our models. Here, it's also an overview of the experiment. So first we had the different data sets, then we had different time windows because we had to segment our PPG data. We selected a few filters to use on that data, and we decided if we wanted to remove motion or not. And then we use an algorithm to detect the different cycles of the PPG signal. The motion removal actually plays a huge role here, especially in the 24 hours experiments, because people are moving and then just going about their lives. So it's something really interesting to look at. And I think it's already known that the PPG data is actually very prone to artifacts, especially during movement. So that's why we have that step in our experiments. So here I just wanted to show, I think Professor Ding already showed a few features. We basically, for this study, we only use time domain features. So here we have one cycle represented from one of our data sets, and here the different features we use in the time domain. We have tried other features in different experiments, but for this one, we mainly focus on the time domain features. And this is just a representation what our window, because I said we use 15 seconds, 30 seconds, 5 seconds windows. This is how it looks like. So a bunch of cycles from the PPG data. And then from those cycles, you can actually extract the features I mentioned, and then you can average them, get the standard deviation or variance. And then you can use that to feed our different models and then get the blood pressure estimation, both for systolic blood pressure, but also for diastolic blood pressure. And here we had these two questions, right? So which model would perform better in our data set and which parameters we should select from the different ones we have tried. And the models we decided to use were models that were currently being used in the literature. So basically Bayesian machines, random forest, a linear regression. And we also had something we call dummy models. So it was a model that just predicted the mean. So we wanted to see if we could be better than that as well, or just not be better, but what are the behaviors of each of different models. And we try to approach those questions with a very kind of, I would say, statistical way of looking at things, especially due to our own backgrounds. So we had a thing, like we did a lot of experiments. So this is 18 combinations of different parameters, right? And the models we use, and we use the mean absolute error as our evaluation metric. And then we draw some expiration. Oh, sorry. I think, yeah, sorry. I think one slide is in the wrong order, but I wanted to show that we draw some inspiration from like statistics or clinical trials and biostatistics, where we treated a model of like a treatment, and we treated the experiments are different patients where this treatment was being applied, and we used the mean absolute error as our measure variable. And in this way, we could actually measure how well or how bad our models perform. So if I go back to the slide, it should have come after. Here, those are the mean absolute errors we obtained. So basically you can see LGBM performed a bit better than the others, except for this last experiment where we had our heart 24 hours and diastolic blood pressure. But then using this kind of analysis, we could see if that was significant or not. So basically combine all of this in a table to see basically the p-values are represented here. We wanted to see if there was a significant difference from one model to the other. So if you focus on the line of the LGBM, which was our best model, you can see that it actually outperforms almost all of the models except for the dummy model. So basically our model was as good as a model that predicts the mean, which is interesting. And in the second case, it actually outperformed all the other models. And even for the random forest, it was basically kind of the same, I would say. And then because of that, we decided that the LGBM was the model that performed better. That especially for the 24 hours experiment, not so much for the stress test, but since it performed as good as the dummy model, we decided to keep it as our kind of winner or winning model. So after we have selected the best model, we decided to, okay, now that we have it, we are going to select a different parameters based on that model. So here we can see our experience again, but this time, instead of using all the models, we use only the LGBM model, still using the mean absolute error as our evaluation metric. And here we did some analysis of variance between the different parameters. So either them by themselves or a combination of two of them, like bandpass filter, motion removal, time window, and bandpass filter. And lastly, time window and motion removal, both all of them using LGBM. And we realized that interaction of time windows and motion removal was the one that actually made a difference. And also that a 15-second window was the one that actually worked best for most of the experiments. Because of that, we decided to keep for our HYPE 24 hours experiment, the 15-second windows for all the other experiment also. But for the 24 hours, it was clearly important that we did some motion removal. So not all the data was used because there had too many artifacts. And we ended up using no filter because actually the data, we used the Empatica E4 device, the one I showed in the beginning, and the data was quite fine. And for the stress test, we also select 15 seconds. Then no motion removal was necessary because people were actually at rest when we took their blood pressure and PPG data. And we kept with the Chebyshev second filter. That's the one that was actually pointed in the literature as the one to use. And there was no statistical difference actually between any of the filters. We could actually have used no filter at all, but we decided to go with this because for the other data sets later, we had to use a filter, and this could be used in all of them. After we decided which model we wanted to use and which filter, which parameters, we applied this model in the other data set. So on the left-hand side, you can see here the evaluation or evolved data set with normotensive subjects and the bigger data set with normotensive and hypertensive individuals. We have done our experiments using leave one subject out validation because we believe when we train a model and we want to apply it in a different, usually subject or a different population. So we want to make sure it is as the most robust as possible. And you can see here that in general, we have kind of high standard deviations and also high mean absolute errors, but this is very consistent to the literature for all the experiments that use this kind of experiment. But we were wondering what happens if you combine, if you divide patients into training and test set and mix them up. And we performed a different type of evaluation, a k-fold cross-validation, but mixing the patients between the training and test set. And clearly you can see that, of course, the mean absolute error goes down, especially the standard deviation goes down. Some people call this as a calibration procedure. And then they say, okay, if you have data, a bit of data from each individual, you can improve your models. But in general, we prefer to use this, the leave-on subject-all validation to make it more robust. It's also possible to add a calibration feature in the models. In this experiment, we don't use it, but we tried it later in some other experiments, and then you can actually see a huge difference in the model performance. But anyway, for this experiment, we don't really achieve the error rates as proposed by the American Association of Medical Instrumentation. So there's still a long way to go and still need to look into more features and different relationships and different models for blood pressure estimation. And I think that's all. And thank you for your time. This is my contacts also if you want to contact me later. Thank you.
Thank you very much, Ariane. Great talk. Great to see the attention that you paid to each of the steps in estimating blood pressure. And we have questions on a couple of those steps. So firstly, Serena asks, how did you perform motion artifact removal?
Good question. There are many ways. In our case, for the Empatica device, we actually had accelerometer data. So we actually measure the acceleration, and if it was higher than a certain threshold, we would remove that whole segment. That's how we did it.
Brilliant, thanks. And on the filtering step, Itzel asks, why did you choose a bandpass filter as a feature for the model? Perhaps maybe worth clarifying whether or not it was used as a feature for the model.
Oh, yes, sorry. It was not a feature. It was a previous step in the pre-processing pipeline. And why the bandpass filter, we were looking to the literature and they were the most used ones. So we were trying Butterworth filters and Chebyshev filters. And yeah, that's why.
Thanks very much. Ramu asks, could you explain how you performed the stress tests?
Yes, so this stress test was done in the hospital, of course, especially because the subjects were hypertensive. So they were observed by a doctor, but they were measured. There is a special kind of treadmill that they can go into and then measures their heart rate. And they do it for a few minutes until the heart rate reaches a certain level. And they do this until that, or until 5 minutes, if I'm not mistaken, then they sit down, and that's how it's done. And usually the blood pressure goes a bit higher. And we want to see actually this variation of blood pressure.
Thank you. And Ramu also asks, and I might add to the question, Ramu asks, could you elaborate on dummy models? And I would add as well, would you remind us what the LGBM stands for?
Yes, I'm sorry. I think I was a bit too fast on that. So the dummy models, it's basically a baseline model you can use. And in our case, we just selected a model that always predicts the mean. So basically, if you have something and you say, okay, please always predict the mean of this time series or this data set, that's the dummy model we use, but you could use different ones. Something predicts the median. I don't know. There are other options, but the ones we used was one that performed just predicted the mean. And the LGBM is actually stands for light GBM. So it's a variation of the gradient boosting machine. So it was developed, if I'm not mistaken, by a team at Microsoft, and it's actually pretty good in general and pretty fast. And it has been used a lot in the field of kind of clinical care and for clinical variables.
Thank you. And Alex just adds a small comment saying it's the mean error rather than the mean absolute error that's used in the AAMI standard.
Yes, that's true. True. And that's something we also noticed, but also the problems with the standard is there's still a discussion, I think, among how to actually evaluate machine learning models for blood pressure estimation. We decided to use the MIE just because of the nature of the measurement and to compare to other scientific work. Maybe I should not have used the AIME since they actually use mean error. But yeah, thank you.
Well, may I thank you once again, Ariane. Great talk, really eye-opening to see your the attention you paid to each of those steps in the processing pipeline. Gives us plenty of food for thought, I think. So thank you once again. So for our final speaker, Serena Zanelli is going to present. Serena, I will just spotlight you.
Thank you.
So Serena, just to introduce you. Our next speaker is Serena Zanelli, a PhD student at the Université Sorbonne, Paris Nord in France. And Serena works also for AxLife, who have developed the PopMetra device for PPG-based assessment of cardiovascular risk. Today, Serena will present a deep learning approach to detect signal quality from clinical to non-clinical PPG devices. Serena, thank you very much for speaking to us today. We're looking forward to your talk.
Thank you very much. So everybody see my slide? Is it fine? Yes. So thank you, Peter, to invite me to speak in this webinar. I'm Serena Zanelli, as Peter just said. I am a PhD. Let's do this. I'm a PhD student in University Paris 8 and Telecom Paris. I collaborate with XLive. There is a small French startup that produces medical devices that use PPG signal to detect cardiovascular disease. And today I'm going to speak about PPG signal quality. So I imagine that everybody knows what is PPG, but I'm going to do a small introduction anyway. So PPG is an optical measurement of blood perfusion in the skin. It is composed by an LID and a photodetector. The LID emits light. The light is partially absorbed by your tissue and then reflected or transmitted, depends on the technology that you use. And so let's use pointer. You obtain a PPG signal that is like that. PPG can be decomposed into two main frequency. We have higher frequency in which information about heart contraction are contained, and we can see the systolic point, the carotid notch, or heart rate. While in the low frequency information, we have, for example, the respiratory rate. So PPG is a non-invasive technology since it uses LID and a photodetector. It's cost effective because the hardware is not expensive at all. It is easily embeddable in different devices. Nowadays, we can find it in smartwatches, wristband, sport tracker, and in addition, it can be acquired in several anatomical sites. For example, it is usually detected in finger, wrist, but it can be acquired also on the head and on the feet. The only condition is that the skin has to be thin enough to allow the light to reach the pulsatile component. So we said that PPG has a lot of advantages, but it does have some limitation too. First of all, PPG is hardware dependent. This means that based on the LID and photodetector that we choose to use, we will have a different PPG tape. It depends on, for example, the wavelength. If we use a red, if we use an infrared, if you use a green light, we will obtain different answers. It depends on the position, because if we use PPG from the wrist, we will have a certain kind of PPG shape. If we use clinical finger PPG, we will obtain another shape. But the most challenging limitation, as the other two speakers already said, is that PPG is easily corruptible by noise. When I speak about noise, I speak about external factors such as temperature, light, external light that can be detected from the photodetector, for example, but also I'm speaking about subject moving. Let's say that we're doing an exam and we are in a clinical condition, the subject is on resting, so it's more likely we will have a clean PPG. But if we're doing an analysis of a 24-hour, with the subject is doing his life, so he's moving, maybe he's running, in that case, obtain reliable analysis is very complicated. As we can see in this figure, this is a signal acquired on the same subject. And in this part, the subject is probably not moving. So we are gonna estimate the heart rate, and the 88 BPM is a physiological value. So everything is fine. But as the subjects start to move, we obtain a heart rate that is 100 BPM. It's still physiological, but it doesn't correspond to the real signal. So we do have an error. And since we are in a medical device domain, if we have to take a decision based on a simple parameter such as the heart rate, based on the analysis that we're doing, we have to assure the patient that the measure is reliable. That's why PPG signal quality is kind of a basic step, but it's very important to do. So when I speak about quality assessment, in my mind, it is composed by three main blocks. First of all, we want to understand if the PPG is high quality or not. So our model has to be able to detect, for example, in this case, if the PPG is corrupted or the PPG is good. The model has to be generalized over different situations because, as we will see, different devices produce different PPG shapes. So we would like to have a model that is able to detect whether or not the PPG is good independently of the device. This is the work that I'm going to present. Then I'm going to suggest you some article because they cover parts that we didn't cover yet in our project, and it's different condition. What if the signal is pathological? Let's say that I want to assess quality PPG in an atrial fibrillation situation. That is very challenging because atrial fibrillation modify the PPG shape itself. And then we reach the explainability. Since we are in medical domain, we need to know why our model is taking such a decision. And explainability is fundamental to validate deep learning model for medicine. In our case, we studied for our study, we used 3 different data sets. I'm going to start with the main data set that is composed by PopMetre signals. PopMetre is a medical device that is mostly used in a hospital or general practitioner. So they are mostly high quality. The subject is at rest. It is sampled at 1 kilohertz and it uses red light. The quality of the PPG is very good. We have movement, we have noise just if the patient is moving. The subject is composed by 500 subjects, so it's this data set is composed by 500 subjects, so it's a quite big database. Then we use 2 smaller data sets because we want to understand. For deep learning, we always read that we need a huge quantity of data. However, we wanted to test what is the minimum size of data that we needed to train a deep learning model. So we acquired 2 other data sets. One is made with iPhone camera. So we process the signal from the video to the signal. And then we use the E4 Empatica that is a free PPG signal. And we did not use any filter because Empatica gives signal that are already filtered. We use a combination of red and green LIT. As you can see in the figure, PPG from Empatica, PPG from iPhone, and PPG from PopMetre, they are, I can see there is a PPG, but they are quite different. Clinical PPG, they are very well rich in detail. We see the systolic and the diastolic, the necrotic notch, while in the wrist, for example, most of the time we don't have a very well-defined necrotic notch. To detect the quality of the signal, we decided to use a CNN architecture. Why we decided to use a CNN? Because we wanted a non-feature-based approach. So convolution allows us to not choose a feature, but it extracts this feature itself. And in addition to that, we use a single pulse approach. That means that the model is trained to judge pulse by pulse. We do not need a long registration to assess if the pulse is good or not, because we're not working on a global vision. We really want to check if pulse by pulse the signal is good. Why we do that? Because in this way, the model can be embedded in several applications. We do not need a long registration to make the model work. So it's a basic architecture, CNN, 4-layer, and it has been optimized with Talos toolkit in Python. Our experimentation starts with training the CNN model over the bigger data set, and then we use this baseline CNN model and we assess transfer learning to check the quality of the PPG in the other data sets, DB2 and DB3. In order to assess if transfer learning really enhances the performance of the model, we also train 2 parallel models, the same exact model, but from scratch. So we don't take the weights of the CNN and we fine tune them, but we start the training from random weights. So our model reached an accuracy of 99.8 on the main dataset, the clinical one, the one taken with PopMetre. And so what's the result? The result is that starting from 4% of the available data, the results between the fine-tuned and the original model, they are comparable, both for DB2 and DB3. So both for starting from the baseline model, clinical, to the non-clinical, so smartwatch and Envatica. The take-home message is that with an amount of 1 minute of PPG, we can enhance the accuracy of the model from 86 to 93%. This means that we could use this model or those kind of models to obtain personalized medicine. It means that after 1 minute of usage, the user could already have a model that learned the PPG shape from the subject. I spoke in the beginning about pathological signal or particular conditions. We did not access the model performances on pathological signal, but I suggest you to check a supervised approach to robust photoplethysmography quality assessment from Pereira, in which they propose a supervised approach to detect quality in presence of atrial fibrillation. If you can see here, we have a normal non-pathological PPG signal, and here we have a non-pathological PPG signal with noise. As you can see, noise is quite easy to identify, even though I'm not an expert, let's say I'm not a clinician, but I can say that here something bizarre is happening. Here we have an atrial fibrillation, and already it's kind of way different from the normal PPG. I let you imagine what it means to detect quality on atrial fibrillation PPG signal with movement. And in this case, they need to use a gold reference, a gold standard like a reference as the ECG, because it's too difficult, or for example, the accelerometer, as she said before, to detect the PPG quality. Another topic that is very important in medical device is if you want to validate your model and you want to sell your model on a device, you need to be able to explain why your model is taking some decision. And in this paper, atrial fibrillation detection from raw photoplethysmography away from a deep learning approach, they use deep SHAP to visualize model attention. It means that we are able, with different models, there is silencing map, attention map, gradient, GradCam, depends on the model that you're using, to understand what points of the signal are interpreted by the model as positive, means, yeah, this is a good high quality, or negative, saying, no, this is not high quality PPG signal. This could be like a first step in order to understand, or like, let's say, take a model and let it be human-like interpretability. So I think that you like your talk, and if you have any question, please do.
Thank you, Serena, very much for a very interesting talk. We have some very helpful questions, which start off by looking at trying to understand a bit more about the approach you've used, and then move on to kind of the bigger picture. So just to understand a little more, how did you label PPG signals as good or poor quality?
They were labeled visually, hand by hand, by a clinician.
Fantastic, by a clinician. So that's Zyrong's question. Okay. Talansh asks, and I'm interested in this as well, if you compare your approach to a feature-based approach, for instance, extracting features and then using a machine learning model, Talansh asks, what features might you use? And I would ask, do you think one approach, deep learning or feature-based, is better than another, or do we not know? Or...
Yeah, So actually, before choosing the CNN approach, we tested several machine learning because, yeah, that's the street that you do when you want to test, when you want to propose a new approach. And we tested also several features such as, I would say that the most important thing is the presence of the systolic, diastolic, and dicrotic notch. The main problem is that assessing the presence of the dicrotic notch with a feature is very difficult. We try to use the second derivative, we try to use several approaches, but we obtain, I mean, you always obtain a value. So you don't obtain a value that is outside your interval, but sometimes that value that you obtain is not corresponding to anything physiological. So that's why, for example, we tried also supervector machine random forest, CNN overcome all these, the other method. I hope I answered to everything.
Fantastic. So it's the systolic peak, diastolic trough,
Yeah,
and the dicrotic notch.
yeah.
Are challenging. They're the important ones, but it's challenging to get particularly the dicrotic notch as a feature. Great. So moving on to the bigger picture, Talansh asks, how confidently can you use this model in real life medical devices, considering the size of the data set?
So actually, there is a paper that is just been published. I don't remember the author, but I can send it to you. Let's say that the deep learning model that has low parameters, and you're using a very small CNN model because they just have 4-layer and very few filters. They perform quite well on small data sets because the amplitude of the size of the data set should be proportional to the amount of parameter that you have to train. So actually, I'm quite confident because we don't use a very large CNN net.
Brilliant. That's very helpful, how using a small CNN increases our confidence. Okay, so Alex asks, what about the accuracy of your model for windows where there's only a relatively small amount of artifacts, such as only 5% of the window length? And perhaps just remind us, you were looking at each individual pulse wave, were you?
Yeah, I didn't understand, sorry. So he's fine. What's the question again?
So I think Alex is suggesting, let's say we have a 10-second window where there's only half a second of artifact.
Yeah.
How well would your model be able to detect just that very short artifact?
It's quite good, actually. I don't know if you, and maybe I can share again my screen. Yes. So this is actually the model prediction. The red part is predicted by the model. As you can see, like the only artifact is composed by this part. So the model is actually quite precise. And when we do transfer learning, as you can see here, like without transfer learning, so using the model that is trained over the bigger data set and then testing on the other data set, we don't obtain a very good result. But when you do transfer learning, we are able to detect that this is noise. Even though we still have a peak, it could resemble to a PPG shape.
Fantastic. We have two final questions. So firstly, Alex also asks, what's the proportion of artifacts and high quality signals in your data sets?
So it's 50-50.
Great, thank you. And then Talansh asks, which is a very helpful question to finish on, perhaps the most challenging part, how would you try to ensure that we're not classifying true physiological changes, and you mentioned atrial fibrillation in your talk, as poor quality PPG?
Yeah, that's very challenging. And that's, I said, like when we have pathological signals, we are not able to detect the quality so far. I think you should train another model. And for example, let's do one step, it's quality, non-quality. And if it's non-quality, then you judge again if it's pathological or just noise. That's the street I will go through.
Fantastic. That's a very helpful approach, taking that two-step approach.
Yeah.
Well, thank you very much, Serena, and thank you to all for your very helpful questions. Fascinating talk, and good to see the deep learning approach alongside the feature-based approaches in our first couple of talks. I'll draw today's webinar to a close by extending my thanks to all three of today's speakers for the fascinating and informative talks, thanking the Institute of Physics and Engineering in Medicine for hosting today's webinar, and thanking you, the attendees, for participating and for your very helpful questions.
Thank you
Thanks
again.
very much. I'll draw us to a close.
Thank you. Thank you, Peter.
Bye.
Thank you all. Nice to meet you. Goodbye.